Good morning. My name is David Finlayson, and I'm Chief Scientist for Chesapeake Technology. This week, we're going to talk about the new Geodesy engine in SonarWiz and spend some time talking about just what exactly Geodesy is and how it's used in SonarWiz. Next, March 14th, we've got mag updates. So changes, we've been doing a lot of work on the magnetometer module in SonarWiz. So in 2 weeks, same time, you can come back and hear more about what we've been doing there. And then on March 28th, we're going to talk about some new bathymetric utilities that are available in SonarWiz. And finally, the end of the series is April 11th. So that's not March anymore, but we'll do integrations with Terradepth and Google Earth and other third-party software that SonarWiz is designed to work with. So March Madness, for those of you who aren't in the United States, this is the time of year our college basketball teams all go head to head and we find out who the best basketball team in the nation is. I put this picture of a basketball on here, and I didn't realize until just this morning that it's an elevation basketball, which is very appropriate because today our topic is not basketball, but how we describe the Earth and how we convert it into useful measurements in SonarWiz. Okay, so today's presentation is about 45 minutes, and I'm going to talk about two different topics. The first is what is a terrestrial coordinate system, and I'm going to cover things like the shape of the Earth, what is a position, how modern GNSS coordinate systems work, and a little bit about geodetic transformations, at least the most popular ones. And then we're going to switch to the SonarWiz interface and talk about some changes we've made, big changes that we've made to the geodetic engine in SonarWiz with the release of 7.10. What that means for you going forward, how you're going to, talk about backwards compatibility and forwards compatibility between projects, and then walk you through actually using the new engine. So how to define a coordinate system, how to transform your data, and creating custom coordinate systems when they're necessary. Hopefully they'll be less often that you actually need to create custom coordinate systems, but I'll talk about all of that. And then finally, I'm going to have some special notes, spatial notes for bathymetric projects. So I am not a geodesist, and while my history with geodesy goes way back, when I first started working as a science as a graduate student, I was working in a project for the US Geological Survey where we created one of the first digital elevation models of Puget Sound in northern Washington. And that project required marrying together over 300 different independent sources, most of which were taken from paper maps and charts. And there was some LiDAR. This is the first, this is 25 years ago. So there was the first flights of LiDAR were being done. We had nautical charts that were mean lower low water. The LiDAR was in, NAVD 88. I had to teach myself how to marry together all the different datums and vertical elevations and everything. And it was all had to be done by hand because this was in the early days of computer mapping. So from that point forward, I also went to the US Geological Survey and realized there was a lot of confusion about all these topics. And we organized a conference between the US Geological Survey, the National Ocean Service, and the National Geodetic Survey. And we brought all of these teams together. And to my knowledge at the time, it was one of the first times that all three of those organizations have been in the same room. And surprisingly enough, the National Ocean Service folks and the National Geodetic Survey were on the same campus, but they had never talked to each other. So the guys who did the tide stations were not talking to the guys who did the benchmarks and set up our vertical system for the nation. And the premier topographic mapping agency in the country, none of us had all talked to each other. So it's not surprising that there's a ton of confusion about all this. And things have changed dramatically with the introduction of satellite surveying. And as you are trying to make your data match up with legacy data that you collected 20 years ago, there's a lot to know. And I'm hoping that in presenting this this talk, that'll clarify some of the some of the lingo. There's tons of acronyms and all that kind of stuff. I shared a really well done document that was put together by the Ordnance Survey of Great Britain about kind of an introduction to all of this stuff. And I stole figures and the topics liberally from this, a guide to coordinate systems in Great Britain. And if you look in the handout section of the webinar, GoToWebinar, I've shared this document with you. Some other resources that I leaned on heavily, the National Geodetic Survey of the United States has a nice web page with a lot of figures. And then another interesting one that I leaned into is this simplified transformations from ITRF to ETRS 89 for maritime applications. And this was done by the Survey of Sweden. It's in English, so you can read it. And then, of course, I just plowed through Wikipedia looking for figures and things like that. But almost all of the figures are taken from these sources. And I tried to put notes in where I got it from somewhere else. So one of the things, to start things off with, there's a lot of myths about coordinate systems. One of the first myths, and this is all from the Guide to Coordinate Systems, is that a point on the ground has a unique latitude and longitude. And as we'll see later in the talk, the positions that we give to a point on the ground, so if we have a particular latitude and longitude and we plot it on the ground on a map, we will actually wind up with different positions depending on which coordinate system we use. So here's an example in this figure here where there's 3 points with the same latitude and longitude plotted over the Ordnance Survey headquarters in Great Britain. And one is in the Ordnance Survey of Great Britain of 1936, one is in ETRS 89, and the other one is in ED 50. So the exact same position plots, there's a 300-meter difference between where these things plot. And we'll talk more about where that comes from in a few minutes. So myth number one, a point on the ground does not have a unique latitude and longitude. Myth number two, a horizontal plane is a level surface. Now, intuitively, we know that if you put a flat surface on the round Earth, that it cannot be correct. The Earth is round, so and gravity works no matter where you are. You know, as kids, we used to joke that if you were in Australia, how do you keep the Australians on the Earth? They would fall off, but that's not the way the Earth works. Gravity goes towards the center of the Earth. So a level surface is not a surface that is flat. It is a surface that represents a gravitational potential. And if you plot a level surface like sea level on the Earth, it looks like this blob on the right. Now, this has been greatly exaggerated, but it is anything but level. So here we've got the United States. There's big bumps over the Rockies. There's holes off the coast of Mexico and the Baja Peninsula. And you can see it. Big mountain ranges cause wrinkles in this flat surface. If we had a perfect, if we had an ocean that no land surface whatsoever, and the Earth's core was completely uniform everywhere, then you would have a flat surface. But because it's made up of continents and they have different densities and there's mountain ranges and there's all this differences in density, there's going to be different gravity potentials. So a level surface does not exist. Myth number three, the true coordinates of a ground point do not change. Now here, if we put a stake in the ground and we do exactly this, and we say this point is going to be a latitude and longitude X, what happens with plate tectonics is that the whole system is moving and shifting. The surface of the Earth is moving constantly, and each of the plates is moving in different directions. So it's impossible to come up with a coordinate system that works everywhere and does not move. So if you come up with a coordinate system that represents the whole Earth and is fixed to the Earth, then the continents are slowly drifting underneath them. If you try to fix a continent system to a plate, like snapping it to North America or snapping it to the Eurasian plate, then all the other plates that are not the one you're fixed to are moving in relative to that. So, and these things are measurable. So we have, for vertical, I have tidal fluctuations, which are up to 1 meter a day. The relative motion of the continents in some places is 10 centimeters per year. These arrows, this one down here is 2 centimeters per year. So some places are moving dramatically. So here, the west coast of the United States is moving at 4 centimeters per year. Huge chunks of Europe over here are moving at 2.5 to 3 centimeters per year. And this is parts of Australia are really moving quickly. And this is all relative to ITRF. So myth number 3, true coordinates of a ground point do not change. They do change. And they change in the vertical here. So this is a plot of the vertical uplift underneath Scandinavia due to isostatic rebound. So that during the last ice ages, the weight of the ice pressed down on the land surface. And even 15,000 years later, it's still coming up. It's still buoying up. And it's many centimeters per year. So the vertical uplift here on the right. Myth number 4, there's an exact mathematical formula to change between coordinate systems. If we had a perfect geometry, we could go from one survey or one coordinate system to another. And then we could just use these formulas up here. This is actually a Helmert transformation at the top. And when you see things like these tables here that list 7 different parameters, I'm going to explain what these all do in a few minutes. But you have this sense that the more digits we put on here, the more accurate it's going to be. But as I'll show you in a few minutes, the problem is that we can never measure any place accurately. And because the two different, we can have, mathematically, we can create a perfect system, but when we actually have a realization of that system, there's measurement error. And that measurement error gets worse the further back in time we go. So using older techniques like theodolites and regular plane level surveying, which the vast majority of the Earth is still using that kind of measurement system, those measurements had error in them. Sometimes they were impressively good, but it was difficult. It's difficult to measure large areas accurately. When we start putting satellites up into space, we got much more accurate. But then we run into a whole new set of problems, and that's tying those satellite measurements back to the Earth. So in SonarWiz, for example, if you pick a coordinate transformation in the new system, you'll see these accuracy measurements here down in this middle column that I'm pointing out with the mouse. And that gives you a sense of not the accuracy of the mathematics of the transformation. This is the accuracy of the underlying realization. So how carefully or how accurate do we, if we measure many different points in this coordinate system, how much basically uncertainty is there in those measurements? And once we apply that transformation to a new coordinate system, which has its own set of measurements, this is the total uncertainty in that transformation. And it can get quite large. In this particular transformation, I'm going from ED50 to WGS84. And some of the better transforms in certain areas can get down to 1 meter, but it can be well above 10 meters in uncertainty in certain other parts of the world, of Europe. Okay, so now we need to talk about some specific terms. So to represent the Earth, we have two different ways to represent the Earth that are in use, and we need to understand the difference between the two of them. The first one is the ellipsoid, and an ellipsoid is a mathematical model which approximates the shape of the planet. So the Earth is a biaxial ellipsoid, and it can be largely approximated with just a simple mathematical formula. However, in real life, the Earth does have a gravitational potential, and we need to know, for example, a surface that we can measure everything relative to, and this is for heights. What do we measure the height of our mountains to, or how deep are the oceans? We need some reference plane that we're going to measure to. Because the Earth is not a perfect sphere, mathematical sphere, we have to use something else. And that's something else we use is a geoid. And what the geoid is a potential energy level of the Earth's gravitational field. So basically, we decided, okay, we're going to measure sea level at a certain place, and we put a stake in the ground there, and we say, what is the gravitational strength at this point in elevation? And then we measure that gravitational potential in other places. It's the way we can migrate an elevation inland where there is no ocean. So if you want to be underneath a mountain and you want to know how, or you're on top of a mountain, you want to know how tall it is, you have to project what would sea level be if the mountain weren't there. If we could pull the mountain out and water flooded in there, where would that be? And when we measure that surface accurately, it turns out that the Earth is not smooth. It actually is very bumpy, and it has to do with the geology of the rock underneath the surface. So the ellipsoid and the geoid are two different ways of measuring the shape of the Earth. So now we've got to answer the question, what is a position? And in geodesy and mapping, a position is a set of coordinates in a clearly defined coordinate system along with a statement of the error of those coordinates. So here's the most common, a latitude and a longitude. And I stole this from Encyclopedia Britannica. And there's also implied in here is the size of the ellipsoid. How big is the ellipsoid? So let's talk about the different types of positions or types of coordinates. Now, the most common is latitude, longitude, and ellipsoid height. So the latitude and longitude are just angular measurements. We're familiar with that. But the ellipsoid height is an important one. So if you have, or spheroid height. So if you have your mathematical surface, it's not going to fit the Earth exactly. So that is our ellipsoid. And then here we have our geoid, which is in red, which is that level surface of the ocean if there were no continents there. The difference between those two is blown up here in this blown up section here is the spheroid height. So latitude, longitude, and ellipsoid height are our normal way of describing some position on the surface of the Earth. But we will often need to translate between these two different points, whether we're on the spheroid or if we're on the ellipsoid. So when you're using GPS to measure your elevations, you're measuring everything relative to the blue circle, the perfect mathematical sphere. When you're on a boat and you're on tides, you're going to be measuring things on the geoid, the red part. And normally it's the geoid elevation that we care about, or the orthometric height. One of the troublesome parts of measuring elevations is that we measure by convention, we measure plumb to level, so, or to the center of the Earth. So here is if gravity were uniform everywhere, a person gravity's always in this, if we were, sorry, I'm jibber-jabbering here. Think about a flat Earth with no circle. If we had a flat Earth and we had a mountain, then gravity would be pointing downward all the time, and you would go up and down, just like this figure number 1. But if you have a gravity potential surface, like a real surface, like this section over here, where gravity is actually dipping, and there's places in like the Indian Ocean, for example, that does this, then gravity is actually moving away in this direction. And so as you walk down and up, it wouldn't cost you any energy to do that. But this, I guess the point of all of this is to say that it is hard to measure vertical. So another type of coordinate is a Cartesian coordinate. This is a more convenient way to do mathematics. And in this, we have an X and a Y and a Z position. And any point on the sphere can be related to this coordinate system. So here we have latitude, longitude, and ellipsoid height, or spheroid height. And here we have an X, Y, and Z. So there's an origin, usually at the center of the Earth, and we have just normal X, Y, and Z coordinates saying how far are we in X, Y, and Z away from the center of the Earth. When you're dealing with geodetic software, oftentimes what happens is they start with a latitude, longitude, and ellipsoid height, and they convert it to an XYZ to do the transformations. And then they convert it back into a latitude and longitude. So geoid height. So I already mentioned this here, but the geoid is the surface that's everywhere level. And that would be this surface here, the brown one. And because the Earth is not a solid or uniform density, that surface undulates and is not perfectly smooth. The ellipsoid, again, is a mathematical surface that best fits this rough, real surface. And the difference between those two is the geoid height. So the difference between our mathematical ellipsoid and the real geoid is the geoid height. And if you add the ellipsoid height plus and subtract off the geoid height, you get an orthometric height. And that is, this H is what we would normally call an elevation. So this blue H is the thing that we're really after. So if you're on the top of a mountain and you want to know how high I am, you're interested in blue H. But with your GPS, what you're really measuring is red H, the ellipsoid height. So in order to get the true height, you would have to subtract off the geoid. So these three things are related to each other. The orthometric height is equal to the ellipsoid height minus the geoid. Tidal datums. So it's almost a whole lecture just talking about how we determined our tidal elevations. In the United States, our National Oceanographic Service breaks up tides into these classes here. There's the highest observed heights, the mean higher high water. So if every day we have semi-diurnal tides, which means 2 high tides and 2 low tides every day, the average of the highest tides would be mean higher high water. And then the average of all the tides would be mean high water. Somewhere in the middle is mean sea level. And then we go down to the low tides. So mean low water and mean lower low water. So if you have 2 low tides, what's the mean lowest water? And then the lowest observed ever. Most of our charts in the US are based on mean lower low water. So when you have a chart data or chart depth, what is the mean lowest water that you see on a monthly basis, and they tell you how much depth below keel you would have given that. Now, the day you show up there in your boat, you might be up here at high tide, so you have to account for the fact that the chart's assuming that on average, the lowest tide we would observe is this mean lower low water, but there could be 2 or 3 meters of tide over the top of that. And then I just drew this in here so you could see where the geoid might fall. So mean sea level at a particular location on the planet is here, but it's affected by things like the shape of the basin that it's in. It's affected by, whether the moon and the sun are aligned with each other or opposite parts of the sphere. So the geoid itself might not be exactly equal to mean sea level, and often it's above or below a little bit. Finally, we have eastings and northings. So these are plane coordinates, or the grid coordinates we would use on a map, things like universal transverse Mercator or something like that. These are the locations with respect to a map. And in the old days, that map used to be a piece of paper that we plotted on the ground. Today, those map coordinates are almost always in a GIS or a piece of software like SonarWiz. So all GIS and SonarWiz work directly in map coordinates for computational tasks. What it does is, rather than having to deal with the unusual shape of the Earth and do calculations using fairly complicated spherical trigonometry, we convert to this plane system using a transverse Mercator projection usually, or some projection that you choose, and that makes that allows us to work in a Cartesian coordinate system where X, Y, and Z have the same length. They're all in meters, instead of having degrees of latitude, degrees of longitude, and meters or radius from the center of the Earth. So choosing a easting or a map projection is really important to getting these easting and northings. Okay, so what is a geodetic datum? Or it's a terrestrial reference system. So for 3D datums, what we need is an origin for our coordinate system, a center point right here, and a direction for the axes. So we have an X, Y, and Z axes and a center of the datum. So that's a three-dimensional datum definition. If we want latitude, longitude, and ellipsoid height, we need all of the above, plus we need a reference ellipsoid. So we need to know how big the circle is. Then we can compute latitudes, longitudes, and a reference ellipsoid height. So geodetic datum consists of a 3D location of the origin, 3D orientation of the axes. We have to agree on where we're going to put the axes, the size of the ellipsoid, and the shape of the ellipsoid. And then finally, you have this local datums for orthometric height. So those are usually measured next to a fundamental benchmark. So these kind of, a terrestrial reference system has to contain all of those things. Now, a terrestrial reference system is kind of an idealized thing. It's something that we can make up on our desk and we can make computer models of. And we decide, for example, WGS84. We set this all up, but in order to actually realize it on the Earth, we have to go out and measure things. And as soon as we input actual reference points, we're no longer dealing with a terrestrial reference system. We are dealing with a terrestrial reference frame. The difference is the system is the idealized version and the frame is the actual realization of it. And there is this is kind of a vital difference between the two. The terrestrial reference system is the part we type into the computer and we assume that this is error-free, but the terrestrial reference frame has error in it, and that is what we actually measure. If this was a little blurb I cut out of this guide, and it's like, to understand this relationship between two coordinate systems properly, we need to understand that the difference in their datums can be given by some exact set of parameters, although we might not know what they are. On the other hand, the difference in their terrestrial reference frames, which is what we really want to know, can only be described in approximate terms with a statistical accuracy statement attached to the description. So the most common and most important terrestrial reference system in the world right now is the World Geodetic System of 1984, or WGS84. This is the datum used by the GPS positioning system originally. It consists of a 3D Cartesian coordinate system, so it has X, Y, and Z axes, and it has an ellipsoid, so that you can convert it into latitude and longitude. The ellipsoid is GRS 80. This ellipsoid is the best fit of the Earth as a whole, but it doesn't fit perfectly in any one spot. The axes of the Cartesian system and all the lines of latitude and longitude are not stationary with respect to any particular continent. So they are stationary with respect to the center of the Earth. And as a result of that, there are places, for example, in Great Britain, where latitude and longitude is drifting by about 2.5 centimeters per year. Hawaii and Australia are moving at more than 1 meter per decade, so that's 10 centimeters per year relative to this reference frame. So this is the starting point. Now there are three important realizations of WGS84 that I want to talk about. There's the broadcast TRF, or terrestrial reference frame, the International Terrestrial Reference Frame, or ITRF, and then the International GNSS Service. So the first one, this broadcast TRF, is the original way that GPS worked. Each satellite broadcasts out its position, or time really, and you measure your position relative to that broadcast reference frame. This is what the military originally used back in the 1980s, and it's been updated over time, but it is actually a fairly low, by modern standards, it's actually fairly low accuracy. The civilian population of geodetic surveys from around the world and scientists put together the International Terrestrial Reference Frame shortly after GPS was introduced. This is not run by the US government. This is something that's run by worldwide standards organizations. And in fact, this has become the most accurate realization of the WGS84 terrestrial reference system. And nowadays, it's actually ITRF defines what WGS84 is. So this is every nation with a sophisticated geodetic survey participates in ITRF realizations. And so now ITRF is WGS84. There's also this IGS system, which is more about an implementation of how Geodesy gets into your receivers, and I'm not going to go into that at all. But what we need to know is that ITRF, originally WGS84 was used to define ITRF, but nowadays ITRF defines WGS84. And you'll see that initially, back in 1994, for example, as WGS84 was getting more and more accurate and redefining it, ITRF was introduced in 1994. And at that time, WGS84 week G730 was equal to ITRF 91 and 92. But these days, somewhere in the 2000s, it actually started to go the other direction, where ITRF was defining what WGS84 is. But today, the latest realization, ITRF 2020, has been defining WGS with week 2238. So these two are now equivalent. And when you're in software, it's important to note that if you have a WGS84 with a particular ITRF realization or WGS84, at the time that these two were defined, they were exactly the same. So you'll sometimes see that ITRF is equal to WGS84. You just have to know which ITRF and which WGS84, because over time they have changed. The only problem with WGS and ITRF is that it's not suitable for mapping. Now, like I already mentioned, that WGS84 position is fixed to the Earth, but the continents are drifting underneath it. So it's not useful for mapping any position, because if you put a benchmark on the side of your property, the coordinates of your property are going to be changing slowly over time, or fast if you live here in California with the San Andreas Fault, or maybe in Europe. So to fix this problem, each national mapping system, or usually whole continents, will get together and they create locally fixed datums. The most common, or some of the most important ones that I'm familiar with, are North American datum of 1983. That's the datum that is fixed to the North American plate. So it's WGS84, and then we lock it down so that the coordinates are not going to change as the North American plate moves underneath WGS84. So that works well for North America. It doesn't work well for anywhere else. It's going to be locked to North American plate. In Europe, the European Terrestrial Reference System of 1989 is locked to the Eurasian plate. So that's the system that you want to use when you're in Europe. And there are others like this. The China Terrestrial Reference Frame of 2000 is locked to the mainland China. There's a new geodetic datum of Australia that's just been published in the last, I think 2020 it came out. It's locked to the Australian continent. So these locally fixed datum are very easy and accurately related back to WGS84 because we can measure the plate motions. So we know that slowly over time they're drifting away from WGS84, and we have formulas that can get us back and forth between them. But it is important to note that, here's this blown up picture of the Earth again. WGS84 or ITRF, those are equivalent, represent kind of a mean fit to the Earth. But when we create these locally fixed reference frames, that is slid around a little bit so that it best fits the continent that it was designed for. Nowadays, WGS80 or ITRF and these realizations are almost always use the same shape they almost always use GRS 80, and they're almost always very close to each other, but they are shifted around a little bit. So here's I found a nice chart that shows the difference, a horizontal difference between NAD 83, which is fixed to the North American plate, and WGS 84 here. And it starts in Florida, it's around 2 feet. And by the time you get to the west coast of the continent here, it's about 4.5 feet, or that's a little over a meter about 1.20 meters or so, if you don't speak feet. I couldn't find one for Europe, but I did find this difference between ITRS and ETRS 89. So remember, ITRS is the more accurate version of WGS 84. And so the difference between that and ETRS 89, it's shifting these arrows. So over time, Europe is moving, I guess it would be moving to the west relative to WGS 84. So if you get your measurements in ETRS, your coordinates stay the same. But if you're using your GNSS system, it is probably recording things in ITRS. So moving from one coordinate system to another, you need a geodetic transformation. And there's a certain, even though the math that does the transformation is probably well known and is accurate, there is an underlying uncertainty to this calculation because each reference frame has measurement error in it. And to give you kind of an idea of how this looks, let's imagine that we have two one-dimensional coordinate systems here. And we have a position that's white, a position that's gray, and a position that's black. So this is a fixed place. And so in coordinate system A, that place was, white was at 4.1, gray is at 9.8, and black is in 12.2. And then we go back and measure white, gray, and black again using coordinate system B. And this time we get coordinates 7.3, 12.7, and 15.0. Same points, just measured in a different reference frame. So we can compute what the average offset is between coordinate system A and coordinate system B, and that would give us about plus 2.97. So to convert from A to B, we need to add about 2.97. But notice that none of the actual points is exactly 2.97. There's measurement error in there. And the standard deviation of the measurement error is about plus or minus 17 centimeters. So if we were going to do this calculation, we would be able to do this 2.97 shift, but we know that there's an inherent 17 centimeter offset that could be present in that transformation. And when you look in the SonarWiz menus and it gives you a list of what the accuracy is, it's talking about this. There's uncertainty in that transformation because no one point was exactly 2.97 meters away. In 3 dimensions, we need to transform, it's a little bit more complicated. This is a nice little grade school example, but in 3 dimensions, we have to use something called a Helmert transformation. And so here we have a point P that's in red, and we want to translate from the green here to the blue coordinate system. And that's going to require an X, Y, and a Z shift of the origin. So we've got to move the origin. We might need to rotate the X, Y, and Z axes. And there might be a little scale difference where we have to increase or decrease the size. So this is the famous 7-parameter shift that you'll hear about. So there's 3 offsets, X, Y, and Z, 3 more rotations. So that's a total of 6 parameters. And then the scale change is the 7th parameter. And then finally, we get to map projections. So map projection is any function that converts ellipsoidal latitude and longitude to a plane easting and northing. And again, like I mentioned before, originally this plane surface was a map. Nowadays, it's our computer software. Distortions of distances and angles are inevitable when you do this. So it is very important that you pick the right map projection for your survey area. The way you gather all this stuff up and name it has been, it used to be quite a wild west of different map projections and datums and all this kind of stuff. But the European Petroleum Survey Group, or EPSG, started a registry back in the late 80s that put all of this together and organized it into a series of codes that we could use that describes each unique coordinate system. So every datum, every spatial reference system, every ellipsoid, every coordinate transformation operation, and all the related units of measurement can now be listed by a simple number that you pick. And we are more and more moving towards the system where EPSG codes define spatial reference system identifiers. So a spatial reference system identifier would look like this. It's an EPSG code, and then just this number, 32610 is the EPSG code for WGS 84 UTM Zone 10 North. And it implies all of this information, which is usually written out in something called a well-known text. So if your software supports EPSG codes, and nowadays probably almost everything does, then you will see you can generate these well-known texts, and this is a computer readable format that says all the information we need to know about this coordinate system. So it gives us the name, the datum that it's on, the spheroid that it's using. Here's the projection, that's a transverse Mercator, and here's all the parameters for that transverse Mercator. So now, to tell a different software exactly what coordinate system and ellipsoid and datums that you're using, all you need is a single number. So that brings us to SonarWiz. So the SonarWiz geodetic library went through a major rewrite this year, or actually last year. But here's the basics. So SonarWiz, I've already mentioned this, SonarWiz uses a planar Cartesian coordinate system inside the program, which means you must pick a map projection and all of this other stuff that's required to create a map projection in order to work inside of SonarWiz. So all raw data must be converted to one of these XYZ coordinate systems defined by spatial reference ID. SonarWiz only deals with the horizontal position. We do not have 3D coordinate system transformations in the program. So this is usually not an issue when you're dealing with side scan or sub-bottom or magnetometer data. We're only dealing with the horizontal part. But for bathymetric surveys, this might be important to you. If you're using the antenna elevation heights, SonarWiz does not convert the 3D heights inside the program. There are really three main areas where you need to specify the projection system in SonarWiz, and that's on project creation, on data import, and anytime you take navigation feeds into the program. Finally, all exports from the program are in the project coordinate system. So once you load data into SonarWiz, when you export it out, it's always in the project coordinate system. So now let me say a few words about why we updated our system. So SonarWiz 7.9 and earlier uses the CS-map library as its coordinate system engine. And over the last, it's been using that engine for almost 25 years. And what we had noticed is that there hadn't been any major developments in the library in more than a decade, and it was becoming increasingly difficult for our small team to support the worldwide changes that are going on to datums and projections all the time. Constantly, countries are updating their coordinate systems, their reference frames, they're improving their ability to measure. Now that we have worldwide ITRF systems, they want to be a part of that. And it was just a huge amount of work for us to try to keep up with all of that. Also, there was no support in this older system for complicated transformation pipelines, particularly ones that have that make use of grids. Instead of just math, they have actual measured grids that are part of the transformation. Australia has introduced a new national datum that requires grids. So we were having trouble supporting all of that. And then custom coordinate systems themselves required a special geodetic utility, which we had to train people to use if they wanted to use it. So as of SonarWiz 7.10, which was released in October of last year, so the last few months, we've switched the geodetic engine to use Proj, which is a popular open source geodetic library it's in virtually every mapping software that you are aware of. It's used by Google, it's used by all of the open source mapping software, and we have reason to believe it's used underlying a lot of proprietary software as well. It is the reference implementation for ISO 19111, which is the ISO standard for mapping. So whenever a new datum transformation becomes formalized, it is first implemented in Proj. It's almost complete support for all the coordinate systems and transformations in the EPSG database, and it is actively maintained. So it is extremely versatile and powerful, and custom coordinate systems can be created using a couple of different methods, which I'll show you in a second here. And then we have to address compatibility between the two. So in general, the legacy systems, so if you create a project in a legacy version of SonarWiz and you want to open it in a new one, the newest version, it is usually supported. And vice versa, you can go backwards if you know exactly what coordinate system you use. And I'll show you that in just a second here. So new SonarWiz and legacy SonarWiz, if they both define the same coordinate system, you can move between versions. If you're using a custom coordinate system, then you need to make sure that the custom coordinate system is defined in both legacy SonarWiz and new SonarWiz to make the transformation. What you'll find is that the new SonarWiz engine, the Proj engine, supports a lot more coordinate systems and transformations out of the box than the old one did. So it's usually a lot easier to move forward than it is to move backwards. You may find that you've picked a built-in coordinate system in new SonarWiz that is not supported out of the box in the old one, and we would have to generate a custom coordinate system for that. There is one exception. So new SonarWiz supports these modern transformation pipelines that are not available and will never be available in old SonarWiz. So if you happen to be using, these are fairly unusual still, but if you're using a modern coordinate system that requires a complicated transformation pipeline, we will not be able to make it work in old SonarWiz. The main difference between CSMap and Proj, and I'm going to actually show you this, is that they use different naming conventions for the same coordinate system. So basically the SRID is used in Proj, is going to be an EPSG code, whereas in CSMap it's a unique name. And the main issue is that you have to make sure that the two match. So let's switch over to SonarWiz here. I'm going to close this and actually walk through some of this. So the first thing I want to show you is how to actually define a coordinate system for a new project. So we're going to create a brand new project using SonarWiz 7.10. This is actually 7.10.02. The new project screen is pretty similar to the older one. The biggest difference is that down here, we've got a new set of buttons here. There's an automatically select the coordinate system, which is the old one, it was a checkbox. And then we've got the browse coordinate system buttons. So let's get a latitude and longitude for a project from one of our files. So I've got some edge tech files here. I'm going to select one of those. It finds the center latitude and longitude is 34 degrees, 182 west. And if we click the automatically select coordinate system, SonarWiz is going to pick WGS 84 UTM zone 17 north. That's the default for this position. Now I know that this actually was collected in the United States in Lake Hartwell in Georgia. And so it's not on WGS 84, it's on NAD 83. So let me correct that. So I'm going to click on Browse Coordinate Systems, and here is where you'll see the new dialog. So we have a list of authorities here. The most common one would be EPSG, but there's other authorities we can use, like if you're familiar with the ESRI's names for things, they have their own codes and their own names for the same coordinate systems. You can pick from there. And then there's a few specialty ones here also. But let's work with EPSG. So if we want to find UTM zone 17 north, we could do 17 north and search. And this will show me all the 17 norths that are available. So I can find NAD 83 UTM zone 17 north is right there. So I select it, And SonarWiz down here shows me all the parameters that are available for this. So this is the wicket that describes EPSG 26917. And it tells me here's NAT83 UTM zone 17. It's going to be NAT83 datum. The spheroid is GRS80. If I scroll down here, it tells me the unit is a meter. So my project is going to be in meters. Basically, that's everything I need to know about this project. So I'm going to click OK. That's what I wanted. And now I've changed it to 26917. Nope, I got to give it a name here. So call this test side scheme. Now, if I go up here and click on my project settings, it shows me everything's pretty much the same as old SonarWiz. It's just now it's going to be using these new EPSG codes. Second place where you need to pay attention to codes or datums is when you import data. So let's bring a side scan file in. So I'm going to select one of these files, and down here we have import Geodesy. In the event that you recorded the data in a different datum than the project, for example, let's say you recorded it in WGS84, or this project's in ITRF, but you want it in ED50 or something like that. You need to tell us what coordinate system you actually recorded the data in. Now this data was in NAT83 UTM zone 17 north, so we're good to go. So I can click that and I can bring it in. Now, SonarWiz will allow you to transform a data or data set into another coordinate system. So right now, we're in NAT83 UTM zone 17 north. We can convert this. Let's say we want to convert to Georgia state plane. So that would be the coordinate system appropriate for this region of the United States. So we can switch that, and SonarWiz will automatically transform the data set for you. So I go to Browse Coordinate Systems, and I can look for Georgia. Oops. Georgia East is what we want. So now the new EPSG code is going to be 2239. It's NAT83 Georgia East, and the new coordinate system is going to be US feet. So if I switch that, I click OK, SonarWiz asks me if I want to convert. And I can say, yes, I do. Now my data disappears because we just converted it into feet, and now we have to recenter. So here we're back, and now if we measure things, it's going to be in feet instead of meters. All right, so that's how you can get data. That's basically exactly the way it used to work. The only difference is that we have this new interface here compared to the old one. Now I want to show you how to create a custom coordinate system. So we'll create a new project here, custom. And I'm going to go Browse Coordinate Systems. And instead of using the defined coordinate system, there's thousands of built-in coordinate systems here, but this time I'm going to create a custom coordinate system. And to do this, for this one, I need to type in some test coordinates. So 48 north and 45 west. SonarWiz uses these coordinates to make sure that the projection you're defining works in SonarWiz and also in the underlying global mapper library that we use for doing image projections. So we'll give this thing a name, and let's call this, I think we'll call it CTI 9709. Now, the first step is to kind of initialize this. There's three different ways you can initialize the coordinate system. The first one you might try is just typing in an existing EPSG code, like 9709, and then you say create from wicket, and this creates a built-in coordinate system. It copies the built-in coordinate system down here, which you can then modify if you know exactly what you want to do. Now, this coordinate system I'm testing here is NAT83 in Canada. So this is the Canadian reference, the Canadian realization of NAT83. It's UTM zone 23 on NAD83. Now, the built-in version of NAD83 CSRS exactly matches WGS84 on the date when it was created, and that's what's built into SonarWiz. But if this customer wanted to apply a time shift, if we know this is actually taking place, in 2022, we want to know what the separation is between the original NAD83 and this new one. We need to rotate in time and shift the data. We're going to have to add some parameters to this. So you can do this in a couple of ways. If your geodesist has worked a wicket for you, you can copy that wicket in here, and now we have this 2 WGS84 parameters. Now these are the 7 parameters that I mentioned earlier that define a rotation and a shift. So if we create from wicket here, it's now going to include this rotation in it. So if you have a geodesist or another software package that produces wickets, you can copy them into SonarWiz and create a custom coordinate system using those. Another way you can do it is to use proj strings. So if we delete this, proj uses a special language for defining a coordinate system. So the first one you enter in is the projection type, and this one will say it's UTM, it's zone 23, and the ellipsoid we want to use is GRS80, and then I'm just going to copy the 2 WGS84 parameter in there so I don't have to type it. There's the 7 parameters. It's the X, Y, and Z shift, the X, Y, and Z rotation, and a scale change. And then we'll say the units are meters, and the type is a coordinate system. If we create a wicket from this is also valid. Down here, SonarWiz is testing to make sure that the latitude and the longitude make a clean round trip through the whole system. And if it passes, you get a green result verified here, then we can create our coordinate system. So I'm just going to give this a good name. So we'll call it NAD83 CSRS, and we'll save it. And now this new custom coordinate system is what we've selected. So here's our new CTI 9709. I click OK, and I have a new coordinate system. Okay, so I've got a couple of SonarWiz projects here, my test side scan project and my custom coordinate system project. So what happens if you open a new project in old SonarWiz? So here I'm going to open up SonarWiz 7.9, and I'm going to open our side scan project. To go to the side scan project, which we define in Georgia State Plane. So if I try to open this now, there's no real issue here, except if we open up this, the old coordinate system engine does not know what EPSG 2239 is. And you'll see that the clue here is it's got a bunch of question marks here. So in order to use this, we have to go into the coordinate system picker here and see if we can search for 2239. So here is Georgia State Plane East, US foot. This is the one we want. So 2239, right there. Notice the difference. This GA83-EF is the way that old SonarWiz used. Its ID is a little bit different than the new one. So we're going to say, it's asking now, do I want to reproject the data? And the answer is no, I'm just redefining it. So now we should be able to zoom to that. And we've opened our SonarWiz 10 project in SonarWiz 9. Now that we've got it defined for SonarWiz 9, if I went back to SonarWiz 10, and try to bring it forward, I'll show you what happens. It's a little bit better. So now, because we knew that SonarWiz 10 was going to open a lot of old projects, we put this dialog in here. It's a Geodesy warning, and it shows you the old project coordinate reference system, which is GA83-EF. That's the old name. And then it tries to find a match in the new EPSG library, 2239. In this case, it found it correctly. It matched it exactly what we wanted, so we can just click OK, and SonarWiz will change the name and open the project. So this project is backwards compatible with the older one. Now, if we had used the custom coordinate system version, we would have to actually go through the whole process of defining a custom coordinate system in old SonarWiz to make that transition work. But if the two coordinate systems are built in, that's what you need to do. All right, so the last thing I wanted to mention is just a few notes about bathymetry. So when you're doing coordinate systems with bathymetry, only a 2D transformation is performed. So it's for this reason, if you're working with antenna elevations, I recommend that you do a 3D datum transformation before you bring the data into SonarWiz. If you're going to use POSPAC or something like that, you can bring in external navigation and work with that external navigation. And this is only if you're doing a datum transformation. So if you're just going to work in whatever you recorded in, if you recorded in NAT83 or ETRF, there's no problem. You can just open that up in SonarWiz. It's only if you're trying to do a datum transformation when you import the file that this 3D comes into play. So if you're working in your raw data, then no problem working with SonarWiz. But if you are doing a datum transformation and you rely on SonarWiz to do that, just keep in mind, it only converts the two dimensions, the X and the Y. It does not do the Z value. For the actual height computations, SonarWiz does pay attention to the survey antenna. It's adjusted for vessel motion if there's a lever arm, etc. You can apply static vertical offsets, and you can also apply vertical datum grids. So if you have a geoid or V-datum grids that you want to load into the program and you want to process down to orthometric heights, you can do that. So just be careful about this one caveat, that if you're doing a datum transformation, that means you recorded in one datum, but you want to process the data in another, you should do that transformation in your Geodesy or in your GPS software, not in SonarWiz for bathymetric surveys. That covers everything I was hoping to cover in this talk. If you have any questions or comments, just go to our website and you go to the support website, and we will be happy to answer any questions you have. Thank you very much. And I hope you join us in 2 weeks. We'll be talking about magnetic updates.